and the impact of the fluid on the production from the pay zone. The primary function of mud is to remove drilled cuttings from the borehole. A clean hole allows the bit to drill into uncut formation rock. Here is an example of what can happen when cuttings are not removed off the bottom. Mud jets out of the bit and moves cuttings away from the bottom of the hole. The mud then carries the cuttings up the annulus and to the surface for disposal. Mud also prevents formation fluids from flowing into the wellbore. The column of mud in the well exerts a hydrostatic pressure against the formations. The hydrostatic pressure of the mud column prevents the formation fluids from flowing into the well. Mud is the first line of defense in well control. As long as the hole is full of mud with the correct density, the well cannot kick or blow out. A kick is the entry of formation fluids into the wellbore. The kick forces the drilling mud out of the hole. If crew members fail to control a kick, a blowout can occur. A blowout is the uncontrolled flow of drilling mud and formation fluids out of the hole. Deep formations can be very hot, and friction from rotating drilling components generates a lot of heat. High temperatures increase drill string and bit wear. Drilling fluid helps to reduce the temperature in the drill string downhole while drilling. Finally, the flow of the drilling fluid through the drill bit greatly affects the efficiency of the drilling process. For the greatest efficiency, the engineer designs the mud circulation system so that 65% of the total pressure loss throughout the system occurs at the bit. Drilling muds can be made up from water or oil. The most common mud is water-based mud. Water makes up the liquid part or phase of a water-based mud. Crew members put clay and special additives in the water to make a mud with the properties needed to do its job well. For example, clays give it thickness or viscosity. The water in the mud may be fresh water, seawater, or concentrated brine, salt water. The one used depends on its availability and whether it gives the mud the needed properties to drill the hole efficiently. The major disadvantage of water-based muds is that they can cause instability in shales. Shales are the most common rock types encountered while drilling for oil and gas. Although additives can help maintain formation stability with water-based mud, drilling with these additives is costly and difficult. In some cases, crew members use oil instead of water as the base of the mud. This is called oil-based mud. Oil-based mud has many advantages. It can stabilize the formation and reduce downhole drilling problems. Oil-based muds do not react with shale like water-based muds do. However, it is harder for the crew to work with oil-based mud because it can create slippery conditions, and environmental precautions must be used. From an environmental standpoint, mud with oil is more difficult to handle because the oil clings to the drill cuttings. The oil must be cleaned off the cuttings before they are disposed of. Sometimes drilling fluid is dry air or natural gas. Here, dry air is coming out of a rig's buoy, carrying very fine drilled cuttings. Air drilling uses large air compressors instead of mud pumps. Drilling with air or gas can prevent formation damage, and can prohibit loss of expensive mud in the formations. And it allows the bit to drill very fast. Downhole conditions have to be just right for air or gas to be usable. For example, the bit cannot drill through formations containing large amounts of water. The water mixes with the cuttings in the air or gas and clogs up the hole. If small amounts of water are present in the formation being drilled, special equipment can inject a foaming agent into the airstream. The foam helps remove the cuttings. In some cases, the rig operator may use aerated mud, which, like foam drilling, helps prevent clogging of the wellbore. From the earliest days of drilling, it has been known that vertical wells are not truly vertical. Some deviation will always occur due to formation effects and bending of the drill string. However, in the 1930s, wells began to be deliberately drilled along a deviated course. Since then, many special techniques and tools have been developed in order to drill directionally with a high degree of accuracy. Directional drilling operations are performed for a variety of reasons. There are two particular types of directional wells which are very common: horizontal drilling and extended reach wells. Horizontal wells allow the wellbore to penetrate a far greater portion of the reservoir. The well can be drilled into the producing formation parallel to the formation's bedding. This significantly increases the section of wellbore that is contacting the reservoir. Extended reach wells are used to access reservoirs that are remote from the platform. This allows multiple wells to be drilled from one platform. Sometimes environmental reasons prevent a rig from being constructed directly over a reservoir. In these cases, extended reach wells can be used to access the reservoir. There are three primary parameters that are used to describe deviated wells: the kickoff point, or KOP, the buildup and drop-off rate, or BUR and DOR, and the tangent angle of the well. The kickoff point is the measured depth at which a change in hole direction should be initiated. The buildup rate and drop-off rate are the rates at which the well deviates from the vertical. These rates are usually measured in degrees per 100 feet of hole drilled. The buildup rate is typically between 1 and 3 degrees per 100 feet. Buildup rates in excess of 3 degrees per 100 feet are termed doglegs in conventional deviated wells. The buildup rate is often termed the dogleg severity. The tangent angle, or drift angle, is the inclination from vertical of the long, straight section of the well after the buildup section. This section of the well is usually limited to 60 degrees inclination or less to avoid hole cleaning problems. It is called the tangent section because it forms a tangent to the arc formed by the buildup section of the well. There are three main types of deviated well profiles. The build and hold profile is the most common one and the simplest to drill. The S-shaped well is more complex, but it is often required to ensure that the well penetrates the target formation vertically. The deep kickoff profile may be required if it is necessary to drill beneath an obstacle, such as the flank of a salt dye pier. This well profile is the most difficult trajectory to drill, since the kickoff point is in deeper, well-compacted formations. When planning a directional well, a number of constraints will be imposed on the well path, including the target location, target size and shape, rig location, and subsurface obstacles.